Good evening and welcome to TIFR's Asset Colloquium. This is a special Asset Colloquium. As you know, the TIFR Asset Colloquia are held on Fridays at 4 p.m. But there is a good reason today to have this very special Asset Colloquium. You will see that, you will hear it in a few minutes. Today's talk is going to be on engineering of carbon nanotubes and their application in Bhabha Kavach. This is going to be delivered by Dr. Kinshuk Dasgupta, who is the head of Advanced Carbon Material Section, G&AMD, Materials Group BARC. Before I go ahead and introduce the speaker, I would like to thank Professor Vandana Nanal for proposing this talk in the first place, and Dr. K. Ramchandran, who helped us reaching out to today's speaker. So let me take a couple of minutes to introduce today's speaker. Dr. Kinshuk Dasgupta joined BARC as scientific officer after completing his bachelor's in engineering in metallurgy and material science from Jadavpur University, Kolkata in 1999. Dr. Dasgupta completed his PhD in chemical engineering from the Institute of Chemical Technology, Mumbai. His PhD thesis, in fact, received Ambuja Cement Best PhD Thesis Award. He visited University of Cincinnati, USA as a Fulbright scholar during 2018-19. He received Young Metallurgist Award of the Year in 2007 by Ministry of Steel, Young Engineer Award in 2012, and Scientific and Technical Excellence Award in 2017, both by the Department of Atomic Energy. Dr. Dasgupta has been awarded Dr. N.J. Suchak Innovation Award in 2019 by the Institute of Chemical Technology, and recently Sant Swarup Bhatnagar Prize 2020 in Engineering Sciences has been conferred upon Dr. Dasgupta for his work on carbon-based nanomaterials and composites, leading to the development of Bhabha Kavach, a lightweight import substitute ballistic resistant jacket for Indian Armed Forces. So I would like to take a break here and congratulate Dr. Dasgupta on behalf of Asset Colloquium and also the entire fraternity of TIFR and, for that matter, TAE for this award, and hence this special Asset Colloquium today. Dr. Kinshuk Dasgupta has filed 2 Indian patents and has authored 3 book chapters and has more than 90 publications in peer-reviewed journals. In addition to Bhabha Kavach technology, he has transferred several other technologies to the Indian industries, including large-scale synthesis of carbon nanotubes and rare earth magnetic alloy powder. Currently, he is serving as the head Advanced Carbon Materials, G&AMD Materials Group, BARC, and he is also an associate professor at the Homi Bhabha National Institute. So with this few lines of introduction, I now request Dr. Dasgupta to start his lecture.
Thank you, Dr. Satyanarayan, for the kind introduction. And good afternoon to all the attendees. First of all, I would like to thank Dr. Satyanarayan and other organizing members of the Asset Colloquium for giving me this wonderful opportunity to present my work in this prestigious forum. And today, I'll be talking on the topic engineering of carbon nanotube and its application in Bhabha Kavach. And before I start my talk, I'd like to acknowledge the contributions of my great team and the mentors and the collaborators at BARC as well as other institute. Now, what is carbon nanotube? So if we take the hexagonally arranged carbon atoms of a single layer of graphite, which we call graphene, and then try to seamlessly roll them into a cylinder, we end up with a carbon nanotube. If it is a single cylinder, we call it single wall carbon nanotube. And depending on how we roll it, it can be either metallic or it can be semiconducting. And if there are concentric tubes, then we end up with multi-wall carbon nanotube. Now, why carbon nanotube is so much important and we give so much importance? That is due to its that excellent properties. So, if we compare the properties of carbon nanotubes along with the other forms of carbon and as well as the steel, which is generally used in our day-to-day life, we see that the strength as well as the modulus of carbon nanotube is the order of 6 to 10 times of that of the steel, having the density 1/6 of that of the steel. So if you consider the specific strength, that is very high for carbon nanotube. In addition, the thermal conductivity, the electrical conductivity, these are excellent for carbon nanotubes. And that is why carbon nanotube has got applications in different fields, starting from composite. In composite, generally it is used as a filler material, in metal matrix, in ceramic matrix, in polymer matrix composite. Then also it finds application in water treatment, gas absorption, energy storage due to its high specific surface area. Carbon nanotubes, they are functionalized with sometimes some specific drug molecules and they are used for drug delivery. It is used for sensing purpose like gas sensing or for chemical sensing, all these things. Then in catalysis like hydrogenation, in field emission. So carbon nanotubes are used everywhere. At BARC, we have several applications of carbon nanotubes, and I would like to focus in few of them. The left side you can see in ceramic matrix, we can add carbon nanotube in ceramic like boron carbide to improve its toughness and its fractural strength. Then in polymer matrix composite like ultra high molecular polyethylene to improve its stiffness, and all these two materials have been used the Bhabha Kavach, which is a lightweight bulletproof jacket. Also, we are working on the doping of carbon nanotube with heteroatoms like boron, nitrogen, and co-doping with boron and nitrogen for hydrogen storage and their kinetic. We are finding out their kinetics. Then we have used carbon nanotubes for metal ion separation, like we have used nicely for carbon nanotube polymer beads for the rare earth extraction, for actinide separation, for water purification. And also there is another form of carbon nanotube which is called carbon aerogel, where the very long carbon nanotubes, they self-assemble and make a 3D structure, and you can use them for various applications like carbon nanotube fibers, flexible capacitor, piezo sensor, chemical sensor, etc. Now, for all these applications where mainly carbon nanotube is used in the powder form, we require large scale production of carbon nanotube also in some economic way. So therefore, to make them in a large scale, we have employed fluidized bed. There are various processes, but we have selected fluidized bed synthesis of carbon nanotube. It is basically a chemical vapor deposition process. Why fluidized bed? Because fluidization gives you the maximum utilization of surface area for a gas solid reaction and also a high throughput. Here we have developed a fluidized bed furnace designed and manufactured. You can see the picture of that, and we can almost produce a carbon nanotube at the rate of 1 kg per day. These two figures are showing the TEM, the transmission electron microscopic image, how the CNT looks, and then high resolution TEM where you can see the number of walls of CNT, and we could get reasonably good purity, 98.5% pure of the sample. Now the basic requirement for making carbon nanotube by CVD, that is chemical vapor deposition, we require to have a carbon source like hydrocarbon. We require to have catalyst, mostly transition metal catalysts are used or their alloys. Catalyst support material for dispersing the nano catalyst on that so that they don't agglomerate. Then we require a carrier gas to dilute the hydrocarbon, and we require some temperature to give the required activation energy for growth of the carbon nanotube. Now in our method, we have used carbon source as acetylene, which is readily available, cheap, as a support material carbon black. I will explain in the next slide why carbon black. It is having beautiful properties and very cheap material. Then carrier gas as argon, catalyst as ferrocene. Ferrocene is a organometallic where you can vaporize them easily, and then on cracking it gives iron nanoparticle. The synthesis temperature has been in the range of 700 to 1000 degrees centigrade, and I have given also the dimension of the reactors here. So why carbon black? See, carbon black is now for developing a nanotube, we require some nanomaterial. Now, fluidization of nanomaterial is a difficult thing because there are agglomeration formation which doesn't allow the nanoparticles to be fluidized very easily. But carbon black is such a material which has a primary particle size of 30 nanometer, but then they self-agglomerate into soft granules with a wide range of micron size. If you see the distribution, that is from 10 to 500 micron and typical size distribution. So you can easily fluidize them. So that is why carbon black has been used. So it is being nanomaterial, but then also it is easily fluidizable. Secondly, the cost is very low with respect to other like alumina, silica, that their costs are high. So what happens? This is a typical fluidized bed furnace here where you can see the blue color. There is the main reaction chamber. There we put the carbon black, and this yellow color is a distributor where from we pass the gas. I'll just show a video which is just typically from some internet I have taken how fluidization happens. If we pass the gas like argon gas we are passing, then this carbon black starts fluidizing in this fashion. Now, what will happen in the bottom where the preheater is written, this part, in this preheater, ferrocene is kept, and this ferrocene, with the help of the carrier gas, the ferrocene vaporizes and this goes into the reaction zone, and the iron catalyst, they get deposited onto the carbon black, and finally when the hydrocarbon comes, it gets cracked and the carbon nanotube, it starts growing. So this is the, in short, this is the way the carbon nanotube grows. Now, as the fluidization is very, very important, so we have to understand whether the bed is fluidizing or not. How we can find out a bed is fluidizing? That is by measuring the bed pressure drop against the superficial gas velocity. So this is a typical plot of a fluidized bed where we can, for this various dimension of the carbon black, we found out the minimum fluidization velocity where the bed pressure drop doesn't increase. So there is a famous equation, Argon equation, from which theoretically we can calculate the minimum fluidization velocity, but practically and experimentally we can find out by this pressure drop measurement. Now, after setting up the fluidization facility, what we studied various parameters to find out the reaction mechanism. Why these parameters are temperatures, then flow rates, carbon black agglomerate size, initial bed height, catalyst concentration, partial pressure of hydrocarbon and hydrogen, and time of synthesis. All these parameters are having some role. Why temperature? Because if we at temperature we can find out the activation energy. So after finding the activation energy, we'll having an idea what is the rate controlling step, because unless we understand the rate controlling step, we cannot scale it up. So for scale up, we need to understand the rate controlling step, overall rate of reaction and reaction mechanism. So after getting the temperature effect, when we see there may be three different kind of rate controlling step. One is external diffusion, another is internal diffusion, and third one may be chemical kinetics. So to understand the external diffusion, we vary the second point, that is flow rates. To understand the internal diffusion, we vary carbon black agglomerate size and initial bed height. Then catalyst concentration and partial pressure, these are varied to understand the effect of the chemical reaction controlling factor. And finally, the time of synthesis, that is varied for understanding the deactivation of the catalyst, because it is not an infinite time period. For infinite time period we cannot synthesis CNT. After some time the catalyst get deactivated. So how it gets deactivated we can find out if we analyze the time. So the effect of temperature, if I see, we can clearly see that this is a typical Arrhenius type plot. The y-axis is the reaction rate, that means rate of formation of carbon nanotube, and this is 1 by T. And we can see there are two regime, clear-cut regime. At the low temperature regime, the activation energy is the rate of 47 kilojoule per mole, and the high temperature regime, it is a 7.6 kilojoule per mole. So we can say at this, below this point, that is almost 803 degrees centigrade, the reaction is chemical reaction controlled, and above that it is diffusion control, because low activation energy means diffusion control. So now after getting this impression, we studied the superficial gas velocity effect, and we are seeing at this two temperature regime, which is low, one is low, another is high, everywhere there is not much effect of the superficial gas velocity on the deposition rate of the CNT. So that means the external mass transfer control is not there. Next, we varied the carbon black size. So if we see at two different temperatures, low temperatures, again after varying the carbon black size we are not seeing much effect, but at high temperature, that is at 1000 degree, we are seeing the effect. So if we remember the first plot of Arrhenius, if you see the higher temperature, there is an effect of diffusion. So here that is coming. So there is an effect of internal diffusion. So due to the change in the size of the carbon black, there is a deposition rate change. So if we plot that, that means formation of the carbon nanotube with respect to change in the diameter of the carbon black size, we can get a straight line, and from there we can have some formula which determines that how diffusion affects. So this is the diffusion control regime. But now after understanding this much, what we can propose, how the process progresses. What happens in a fluidized bed? Typically there are two phases. One is called emulsion phase, where gas and solids are almost homogeneously mixed, and there is a bubble phase. If you see that I am showing that two bubbles where mostly excess gases are there. So what happens in the first stage, the hydrocarbon, that is our acetylene, it transfers from the bubble phase to the emulsion phase. I am showing an arrow, and then there will be a mass transfer from the emulsion phase to the external surface of the carbon black. So if this is a carbon black where these are the primary particles, and this is the iron nanoparticles sitting inside the pore. So acetylene, first step is from the bubble phase to emulsion phase. Next step, from emulsion phase it is coming to the external surface of the carbon black, which is the external mass transfer. And then what we can show after coming, so it is adsorbing, fourth step is the adsorbing onto the surface of the catalyst. So if it is adsorbing, and then after adsorption the reaction on the catalyst surface is happening to produce carbon molecules, means acetylene is breaking into carbon atoms and hydrogen, and this carbon is having solubility into the catalyst of iron. So it is getting soluble, then it is getting saturated, then supersaturated, and once supersaturation occurs, carbon nanotubes comes out, like this carbon nanotube comes out, and then that is the step of nucleation and growth, and hydrogen and the argon, they comes out. That is the fourth, 9th, 10th and 11th, that is desorption of the hydrogen from the other gaseous products, and then the diffusion of the gaseous products from the catalyst surface to the external, just the opposite, external surface of the carbon black, and finally the mass transfer of the gaseous products from the to the bulk emulsion phase. So this is the 11th step. If I summarize the 11 steps, so first 3 steps are diffusion, and also last 2 steps are diffusion. So now we have seen after certain, at low temperature, they don't have much effect on the formation of the CNT. And from 4th to 9th we have we have the effect. So these are chemically controlled. So if I now, if I can have some mathematical model for these steps, like acetylene is reacting with S means a site. So, and it is adsorbed on the site. Then from after adsorption, it can break into carbon molecules in C2, and then hydrogen can come out. And this carbon molecule once again reacting with the incoming acetylene and getting saturated, hydrogen is coming out, and again the saturated one, they can once again react with the acetylene and become supersaturated, and finally supersaturated, it can form CNT and comes back to the saturated state. So only the last step, it is irreversible, all other steps are reversible, and we can have the mathematical equation related to that, and considering each step as the individually rate controlling, we can find out the final equation like this. Why this is required? Because finally we need to plot the experimental data and we need to see which equation it fits, and then we can say, oh, this particular step is the rate controlling step. So now if we see the previous one, everywhere CT means catalyst concentration. So if we see all these equations, they linearly vary with catalyst concentration, which can also be seen in this graph. If we vary the catalyst concentration at to various partial pressure, it is a linear variation, and finally we achieve some saturation value. And when we plot the partial pressure with respect to that partial pressure for the CNT deposition rate and try to fit it, we can see that it is fitting with this fifth one, that is this step. So this fitting is the best fitting, and from there we can tell, okay, the fifth step, that is the dissociation of adsorbed acetylene into the carbon molecule. That step is the rate controlling for CNT growth in a fluidized bed process. So here we can also find out the rate constants, and this we have published in AICHE journal. Also, we analyzed the other published data with our model, and we could find that our model could predict the others data as well. Now, as I was talking about deactivation, so we could find with time how the reaction rate changes, and that also can be put in a mathematical model. So the rate constant can be expressed in this equation, where from you can get the value of the constant. And I am typically showing one TM image where once the catalyst it is deactivated, basically what happens, they are covered with unwanted forms of carbon. So once the catalysts are covered, then it cannot nucleate the CNT. So you can see somewhere the small CNTs have been grown, but finally once it is covered, you cannot see further growth of CNT. Now, how we characterize the CNT after obtaining, the first thing is Raman spectroscopy. It gives a very clear-cut picture about the nature of your CNT. So if it is multi-walled, we get typically 3 peaks, D peak, G peak, and 2D peak. And when it is single walled, this D peak is almost missing, and we get another peak at the low that frequency value, wave number value, which is called radial breathing mode peak. That you will see in subsequent slide. So we get a typical Raman spectrum at different temperature, and we do TG. TG means thermogravimetric. Here we can find how in oxygen atmosphere there is a weight loss, and if we plot the differential, we get typically 2 peaks. Generally, the end of a carbon nanotube, which is a cap type of thing, and some of the defects which are present, that being high energetic area that starts oxidizing first, and the wall of the carbon nanotubes which are well aligned, that starts oxidizing later. So we generally get 1 peak corresponding to the high energy portion oxidation. Second is the relatively stable phase oxidation. And this is the typical TM images of multi-wall carbon nanotube at different temperatures. You can see how they look. And this is the high resolution TM, where you can count the number of planes of carbon which is typically 8 to 13. And if we talk now for the single wall carbon nanotube, so generally another process is followed, which is called floating catalyst chemical vapor deposition. So there we use methane, because why methane? Methane is having single carbon molecule, so controlling the carbon is easy in methane. Then ferrocene is once again used at the catalyst. Then another important material, sulfur, is required for the growth of the single wall carbon nanotube. And then argon and hydrogen, also hydrogen. The hydrogen and sulfur, these are the two important factor. So hydrogen controls the kinetics and decomposition of the hydrocarbon, which is very much required for the growth of the single wall carbon nanotube. So this is typically TM of the that single wall carbon nanotube. Generally all single wall carbon nanotubes, they are present in a bundle. So you can see a lot of single wall carbon nanotubes here. But then in the Raman, we don't see the peak of the D, which was present in multi-wall, and here the RBM peak comes. So by seeing the Raman, you can understand whether the whatever you have produced is single wall or multi-wall. And from RBM also you can find out the diameter of the carbon nanotube. Now, if you see the TG, this is very sharp, and you don't see much, means only single peak is supposed to come in a pure single wall carbon nanotube. Now, if we see the effect of the partial pressure, and then if you remember, for multi-wall, generally this goes on increasing and the rate becomes slow, but this goes on increasing. But in case of single wall, there is a drop in the rate of formation. Typically it follows a different model. So that is why we always synthesize single wall carbon nanotube at a low partial pressure, and we cannot scale up the single wall carbon nanotube production. The rate of production cannot match with the production of multi-wall carbon nanotube. So these are some of the selected publications what we made. Now I am coming to the second part of my talk. Now, after making these carbon nanotubes, as I showed that there are several applications, but this Bhabha Kavach, which is the lightest bulletproof jacket in India. So how we developed this using the carbon nanotube. So I'm giving a basic concept of a bulletproof jacket. It consists of two main parts. First is called soft armor panel, which is a flexible and it takes the body contour. And second is hard armor panel, which is not flexible. It is having some curvature, but it is a stiff material. You cannot further, after molding, you cannot change its shape. So what happens? We wear this jacket. All these things are soft armor material, and this hard armor panel is the insert inside this pouch. So for the low caliber bullets like 9mm bullet or whatever is fired from machine gun or Sten gun or pistol, so that can be beaten by soft armor panel itself, which is called SAP. But for higher caliber bullet like AK-47, INSAS and SLR, you require this hard armor panel, which is put into the insert front, back as well as sides wherever required. Now, what were our objectives? Our objectives were to develop a lightweight jacket. Before it came to us, we were told the jackets were weighing more than 11 kg, 11 to 14 kg. And then, so it was heavy. So our objective was to develop a lightweight material, providing a multi-hit capability so that multiple shots it can take. And third thing, another important thing is called to reducing the blunt trauma or backface signature. What is backface signature? Means even if the bullet is stopped by the bulletproof jacket, the energy which is absorbed, it gives a protrusion towards the backside. So the protrusion, if it is too high, it can damage the internal organs. Even by that, one person can die. So even a bullet is stopped, if the value of the backface signature is high, it can kill a person. So our objective is to reduce that also below 25 mm. So how it is measured basically? So some material, plasticine type of material is put, and then on top of that our panels are fixed and it is hit by the bullets, and whatever impression is coming on the plasticine which resembles our body muscles, so that depth is the measure of the this BFS, back face signature. So as I talked, the hard armor panel basically is a sandwich of two material. The front face, which is the bullet facing face, is always a very hard material, ceramic, and the back face is a carbon nanotube and polymer layered structure. So the philosophy is a combination of a hard face and a tough material to beat the bullet. So initially, by the hardness of the front face should be the more than the hardness of the bullet, so it should blunt the bullet and fracture them, and in that way the ceramic itself get fractured and the bullet is also fractured, and the backing material, which is that red color you can see, these are the layered structure of carbon nanotube and the ultra high molecular polyethylene fabric. So their role is to contain the bullet fragments as well as the ceramic fragment, so that they don't become a secondary bullets. And what is the role of soft armor panel? So soft armor panel basically absorbs the other energy, so it gives you the cushioning effect as well as it reduces the trauma on your body. So if we see the stopping mechanism, if you see, if the bullet comes, it first hits the hard ceramic, it gets blunted and the jacket of the bullets gets ejected, and the core comes and it makes fracture on the ceramic, and slowly it passes through the ceramic and then comes in contact with the backing material, which is a layered structure, and initially few layers they get teared and finally it gets trapped. So that is the steps. So this is same thing by some pictorial, another some views are there. So now how we played with this hard armor panels, and that I'll explain. That just now I told that boron carbide, it is a very hard material, it is a light material, but it is having a low fracture toughness, so it easily get fractured. So what was our intention, that how to improve the fracture toughness of boron carbide? So we utilize different carbon materials, carbon nanotube, graphene nanoparticle, as well as carbon fiber. So they were mixed properly, then hot pressed, and then we made tiles out of them. So this is the extra diffraction showing there is no oxide phase generally which comes into the boron carbide, but here it is absence of oxide, it is showing the XRD. And the Raman spectra, it shows the presence of both boron carbide as well as the carbon nanomaterials. So now I'm coming to the microstructure part. So what happens when carbon nanotube is added and increasing volume percentage, you can see there is a reduction in the porosity. But after a certain volume percent, then once again we see the agglomeration. So that means very high volume percent is not also required. The same thing happens with graphene nanoparticle as well as the carbon fiber. Now I want to compare between these three materials, how the mechanical properties of the boron carbide gets affected. The hardness, if you see, the hardness we reach maximum with CNT addition, but with carbon fiber hardness drops. Hardness being a very important criteria for the ballistic application, so we need to see which material retains the hardness. Then flexural strength, carbon fiber improves maximum, but CNT, okay, this is reasonably well improves, but then graphene nanoparticle, it drops. And then fracture toughness, with carbon nanotube and graphene nanoparticle it improves, but with carbon fiber it doesn't improve that much. So if we optimize, so the optimum composition we came with 5 volume percent of CNT. as I have already shown, we have the capability of CNT of making in large scale. So this gave us confidence. Okay, we can go for a large scale production for boron carbide CNT, this composite. So here I am showing that this is a bag full of boron carbide CNT tiles. And another, you have seen that carbon nanotube is also applied in the polymer. So how it helps in polymer? So this is a DSC, differential scanning calorimetry, where it shows that there is a bond formation between CNT and ultraviolet polyethylene when they are processed up to a particular temperature. And even in the microstructure, we can see between the layers the carbon nanotubes are there, which really makes the ultra high molecular polyethylene very stiff material. So the selected publications are shown here. Now I want to show that what are the stages. So ultra high molecular polyethylene sheet we took, then we did CNT spraying on that, then compaction molding, then we laid the ceramics on them, then vacuum bagging, aramid mapping, and now we came up with this is a hard armor panel. So then what happens before ballistic test? It undergoes various other rigorous tests like conditioning. The hard armor panel, it undergoes a thermal cycling from minus, say it goes up to 90 degree centigrade, as high as 90 degree centigrade, and also it goes to minus 15 degree centigrade. And then there is a tumbling test for soft armor panel, where in a drum it is rotated for 10 days and in the water. After doing everything, they are tested against bullet. That means after they are rotated into the into a tumbler, and after undergoing thermal cycling, and also a drop test, means from a certain drop they are thrown, so that there should not be any crack growth. After this, they are fired with the bullets. So it has to withstand the bullet after all this conditioning. So here I am showing some pictures. See the leftmost side, this is the typically used nowadays, that what CISF was using, what they were having. So this much dent was there with SLR and AK-47, and when Bhabha Kavach was used against them, you can see very small amount of, this is called backface signature. Now in this is level 3. Level I have not explained, because level means the caliber, bullet calibers increases and threat level increases. I am just showing that with respect to the present bulletproof jacket, how is the improvement of the Bhabha Kavach. And when we used boron carbide CNT, almost nil, very negligible. And if I show you the values, you can see the right side is the some other vendor developed, which is market available. Here what Bhabha Kavach is giving, these are the SLR shots and these are the AK-47 shots, hard steel core. And if you can see the bullet fragments, we did after the shot, we did the XRD, XRD, it is X-ray radiography. So X-ray radiography, you can see the captured bullet into the hard armor panel. So this is the Bhabha Kavach developed, and this was handed over to the NSA. The Bhabha Kavach is having different level, means level 3 weighing 4.75 kg, where the existing one was weighing more than 6.5 kg, and level 3 plus weighs 6.8 kg, whereas the existing was weighing more than 11 kg. So here the summary of the weight, how the weight got improved. A large size jacket, less than 5 kg it weighs, it gives a protection against level 3. Level 3 means it gives protection against AK-47 mild steel core bullets, and level 3 plus means it gives protection against AK-47 hard steel core bullets. And then there are something called standalone. I am not going into the details of that. I wanted to only pass on the message that they are very light, or more than 25% light than the existing jackets. What is the current status? We have already transferred the technology of Bhabha Kavach to 5 companies, and more than 150 numbers of Bhabha Kavach we ourselves manufactured and given to different forces for their and northern commands for their field trials, and some of them have deployed also. Then boron carbide powder and hot press boron carbide tiles also TOT under process, and also a large scale production of carbon nanotubes, which I first part my lecture I showed. So that also TOT are available for the companies. Now, after completing successful trials, almost 500 numbers of Bhabha Kavach order is there from Midhani. Midhani has taken the technology, and they have also bagged 5 numbers of that is called BR shield, that is bullet resistant shields. And we recently gave 55 numbers of Bhabha Kavach of the CISF, who are giving protection to BRC. And there was wide media coverage for the development of a Bhabha Kavach also. So once again, before concluding, I want to acknowledge my excellent team members who put their efforts to make this project success. And with that, I must thank all of you for kind attention. Thank you.
Okay, thank you very much, Dr. Dasgupta, for your excellent talk, which covered the science behind this work, which ultimately had its impact, I would say, in the security, or I would say the security of the people who actually are securing this country. And so congratulations for your great work for you as well as your colleagues, and also, of course, once again for your award. Now there are questions, mostly I think on the, I think there might be some questions here too, but mostly on the YouTube. I would like to take one question at a time.
Yeah.
Okay, so let me, yeah, so there is one question from TLMV Subarao. How these carbon shoot particles are reorganized as single-walled, double-walled, and multi-walled carbon nanotubes? Is there a valid mechanism for reorganization?
Yes, there are mechanisms. See, basically, there are well-established mechanism. See, what happens for getting single-wall carbon nanotube, first of all, you should have a catalyst size less than 5 nanometers. And then the rate of supply of carbon should match with the growth rate of the single layer of the graphene layer in the vertical direction. So when your rate of supply of carbon atoms is exactly matching with the growth rate of the nanotube in the axial direction, then you will always get a single wall. But then when there are multiple nucleation sites, and when there is a rate of supply of hydrocarbon is more, then what happens? There will be concentric nucleation. So you get the multi-wall. And when the rate is too high, then you get soot. You don't get any nanotube formation. The catalyst is deactivated by formation of the amorphous carbon for high rate of decomposition. So that means for single wall carbon nanotube, you should have very low partial pressure of hydrocarbon. First, you should have a very less than 5 nanometer size of the catalyst. For multi-wall carbon nanotube, you can have slightly bigger catalyst, and you can have a higher partial pressure. But if the partial pressure is too high, then you will end up with soot.
Another question from the same participant, in the single wall, double wall, and multi-wall CNTs, which is more active and which is having more surface to volume ratio?
No, see, this is if you active means reactive. Definitely single wall is more reactive, and surface area wise, if you calculate multi-wall carbon nanotube can have more surface area, but as they agglomerate, finally when you measure, you get less surface area for carbon multi-wall carbon nanotube and more surface specific surface area for single wall carbon nanotube. But if you geometrically calculate, multi-wall carbon nanotube is having more specific surface area.
One question from Abhinav Chaudhary. As boron carbide used in the making of Bhabha Kavach, which has the ability to absorb neutrons without forming long-lived radionuclide, is it a good shield also against neutron bombs and ionizing radiation?
See, boron carbide is used as a neutron shielding only. As we are from the atomic energy, the boron carbide primary use is neutron absorbing material. So we were having always the technology of hot pressing boron carbide, which is a really difficult technology. Not everybody is having. We had, so that was our advantage, and we could utilize our prior experience into making Bhabha Kavach.
Okay. So, are there any more questions, please, both on the WebEx platform as well as YouTube? If there are some questions, please type in quickly, especially the YouTube. Okay. So, yeah, there's one question that came up. Okay, fine. This is more like a comment or congratulations. This is from Dr. Pitambar Singh. Congratulations, Dr. Dasgupta, for well-deserved Bhatnagar Award. Very nice and informative.
Thank you, Dr. Pitambar Singh.
So, if there are no more questions, so once again, let us thank today's speaker, Dr. Dasgupta, for his excellent work and also for his very nice talk. And I hope it will be more inspiring to other younger scientists and engineers of this country. There is also another comment from Professor Vandana Dhananal. Congratulations, Dr. Dasgupta. Very nice talk. So,
thank you, Professor Vandana, and thanks all for your kind attention. And thanks, Dr. Satyanarayan, for your effort to arrange this colloquium, special colloquium.
Yeah, so it's our pleasure, Dr. Kinshuk, and we are obviously quite excited and very, very nice to actually have you talking here right after your award. And we look forward to much more success stories and also accolades to you in the future. Thank you very much.
Thank you.
Bye.
Bye.